Good morning. This is lecture 5 of the course in mechanical vibrations. First, let me say a few words about what the action plan is for the next 2 days. Remember, we have a test coming up a week from today on Thursday, January 26th during tutorial time. Obviously, you're guaranteed 50 minutes, but I will try to negotiate with the instructor who's in that class to give you an extra 10 minutes. I don't know right now. I have to work on it. So either 50 minutes or 1 hour, depending on how successful I'm going to be in my negotiations with the instructor. Now, uh, it will cover material through Thursday morning's lecture. What I plan to do on Thursday morning in the Thursday morning lecture is try to do some kind of a review, but this is going to happen by doing some extra problems or a bunch of problems. Okay, so that's how the review is going to take place. And of course, I answer any questions that you may have, and I can answer freely. Okay. Uh, Yep. Somebody asked me what the format is going to be. There's going to be 20 multiple choice questions, multiple choice true, false / short answer question, and a problem to do, basically hand calculation type problem. Okay, so let's move on. Let me show you the agenda for today. There is some catch up from last time. There's 3 problems that I wanted to do, but I ran out of time. So I'm going to do those, and then we go and discuss the concept of effective stiffness, effective mass, and also discuss energy methods later on. So here's the problem that we're doing. Suppose we have a situation like this where uh, there is a rigid bar here, massless bar. This bar is massless, and there's a spring there, and there's a bulb sitting at the bottom, the mass, and it's attached to a damper. So what we want to do is to find the equation of motion, and based on that find the natural frequencies, etc. So this is a single degree of freedom because as the bar, this rigid bar, tilts, the entire configuration resets, and you can determine exactly where the situation. Oops. You can determine exactly what the situation is. Uh, by giving it angular displacement uh, to this bar. And what we're going to do is solve this thing using Newton's method, Newton's second law, and in fact, it's more appropriately Newton-Euler method because Newton was the person who came up with the idea of force equal to mass times acceleration, but these are for point masses, okay? If you have a rigid body, then you also have a rotational motion that can be ignored when the masses are point masses, and those derivations, which is basically extending Newton's second law to rigid bodies, was due to Euler. So what we're going to do is to write down some of all the moments about the pivot point equal to the mass moment of inertia about the pivot point times angular acceleration. Now, keep in mind that this this bar is massless. The mass moment of inertia only comes because this mass m is rotating about that point O. And that's why it's equal to just m, the mass times L squared, okay? Here's a free body diagram. Now I also have a reaction force at the support O here, the pivot point O here, but this R is not going to come into the picture because it passes through the point O, and when you take moments about this point, for R is going to be 0, moment arm is 0. So these are the forces. This is the force of the spring. And the reason it's like that is because L1 times theta, if this thing rotates by the amount theta, it compresses the spring by the amount L1 theta. And if you multiply it by the stiffness of the spring, you get the actual displacement. and displacement times the stiffness, and you're going to get the force. The other force that's acting is the mass times g, so the weight is pointing downward in that configuration, and uh, the damping force is just the velocity of this point, velocity of this point times the damping constant. And the velocity of the point is just the L2 times theta dot. The reason is that L2 times theta will give you displacement of this point, and L2 theta dot will give you velocity of this point. So you take the moments about the pivot point. Now, if you say, well, where did these cosine and sine come from? When you look at these, for example, if you look at the spring force up here, the moment arm is actually the projection of this red line on that vertical axis. So if you take L1 times cosine of theta, you get the moment arm due to this spring force. And by the same token, this damping force has to be multiplied by the moment arm, which is that distance, and that is simply L2 times cosine of theta. Mg, on the other hand, the moment arm about the point O is just this length, horizontal length, which is just L times sine of theta. So these are coming from projections because we need the appropriate moment arm. But we know that this course is about linear vibration, and cosine of theta is approximately equal to 1, and sine of theta is approximately theta. Okay, so if you write these things down, this is what you're going to get. And if you clean it up by taking everything to one side, you're going to get the effective mass. This is the mass, effective mass, times the acceleration, angular acceleration, effective damping coefficient, times the angular velocity, and effective stiffness. So it's not only K, there are other things that pop up here because MGL is also restoring force. So effective stiffness times the angle. This is the mother of all equation. And if you want to find the natural frequency of it, take the effective stiffness, which is the coefficient right in front of theta, and divide it by the effective mass, which is ml squared. And there we are. Now, I wrote this thing here for your convenience. Here's the natural frequency that we just saw a second ago. Now, if you want to find the other parameters, such as the damping, obviously there's a damper here, so there's damped frequency. Eventually, this thing will oscillate. The period of oscillation, or the amplitude oscillation is going to get smaller and smaller. But to get that stuff, for example, we need the damping frequency, which is given through the standard formula. And if you take zeta is the effective damping coefficient, which is right there, divided by 2 square root of effective stiffness times the effective mass. So I put the effective stiffness right there, effective mass there, and there's your damping coefficient, damping friction. And if you want to find the damping frequency, you just put it in that formula, and you're going to get some expression of this type. And that kind of wraps up the problem. Now I want to repeat the same. Okay, we just did this, I think. Oh, yeah, I forgot. Hang in there. So I want to do another problem. This is a problem very similar to the one that we just did, except that the pivot point is up there. Once again, it's the massless rod, vertical rod. There is no damper here, and it's hanging up from the ceiling. Okay, so obviously, if you take this mass and tilt it a little bit to the left or to the right and let it go, it starts oscillating back and forth, back and forth. And what we want to do is to get the same thing, natural frequency and the equation of motion of this setup. So the free body diagram is here, and there is a reaction force that is not important because we're going to take moment about that point. It's going to disappear, and let's use Newton's second law. Sum of all the moment equal to mass moment of inertia times angular acceleration, just like before. Now, if you take, for example, this is the spring force, which is that number, times a moment arm, which is the projection of this length A on that vertical axis, And then weight, or the weight has a moment r, which is just this horizontal distance, and it's going to be basically L times sine of theta. Uh, Once again, cosine of theta is approximately 1, sine of theta is approximately theta, because we're looking for small scale oscillations, and clean it up, and you're going to get this. There is no damping here, therefore there is no theta dot. Now, if you take, this is the effective stiffness, spring constant, and this is the effective mass. So to find natural frequency, you do the usual thing: stiffness over mass, effective stiffness over effective mass. There we are. Now I want to repeat this, except that the pendulum is vertically up. You know, the pivot point is down below. This is called the inverted pendulum. You might say, well, what difference does it make? Can I not do exactly the same thing? The answer is yes. So once again, you draw the free body diagram that you see over there, and you take all the moments about the point O. For example, just look at this spring force. It has a moment which is in the clockwise direction, opposite to where you're measuring. Yeah, uh, Opposite to the positive convention that I have here. So it's going to go minus the negative sign, and mg is, now if you look at it, is let me see now for a second. Mg, the weight is going to have a moment that is given right there. And you see a minus sign here. The reason you see a minus sign is that I decided that the angle is measured like that. And therefore, if you take this moment, if you take J about this direction, theta dot, which opposes that, you're going to get a minus sign. You can sort these out by writing it and looking at it in detail. So once again, small angle approximation, cosine of theta is approximately 1, and sine of theta is approximately theta. Uh, don't let some of these signs bother you. I mean, you have to be consistent. You have a positive direction that you took. And then over here, of course, the way of drawing my angle is opposite to that. That's why I put a negative in front of that basically JO times things. Okay, now clean it up, take everything to one side. You're going to get this very similar to what we had before, except that before, when the pendulum was hanging from the ceiling, this was a positive. Now it's a negative, and there's a natural frequency of vibration. There's a fundamental difference between this problem and the problem that we just did. In fact, we can see that if the choices of K, A, M, L, M, and L, and G are such that underneath the radical you get a negative number, and it is possible. In the previous case, it was not possible because there was a plus sign. But over here, if this thing comes negative, this whole thing is totally useless. It's meaningless. Now, what that means is that this configuration is actually unstable, and it doesn't take you much to see, because if, for example, if this spring is very uh, soft, very soft, you know that if you tilt this thing a little bit to the right, it will not oscillate back and forth. It may actually drop, completely rotate and go away from this vertical position. On the other hand, if K is relatively, well, if it's hard enough, stiff enough, then as you tilt the mass a little bit, it begins to oscillate back and forth. In other words, this vertical position is unstable. It is possible to have oscillation there, but for certain choices of these parameters, the oscillations will not take place, and this goes berserk. It's an unstable uh, uh, position. Okay, so what I want to talk a little bit about different ways of putting springs together, because in many of these problems that we do in a course like this, there are multiple springs, and you have to, excuse me, you have to lump them together somehow. So we need to review some of the stuff that we have learned in our first year mechanics class. So if you have two springs like that, these two springs are said to be in series. And the stiffness of these two springs, when you put it together as a whole, as an assembly, is actually smaller than K1 and K2. Okay? In fact, uh, the expression that we were told, if they're in series, 1 over K effective, which are called from A to C, is equal to 1 over K1 plus 1 over K2. And then you solve for K effective and you get this expression. On the other hand, if you have a situation like this, two springs in that configuration, these are called parallel, and the effective spring constant, effective uh, stiffness is just add them up. Okay. So if you look at this situation, we have 5 springs here. There's no doubt that K1 and K2 are in are parallel. So if you just add up the stiffnesses, when you look at K3 and K4, they are in series, so we can actually find the effective stiffness through the formula that we just wrote up here on the top left corner. And now these two bottom ones are in parallel, so you add them up. And finally, these two springs are in fact parallel, in spite of the fact they look like that, but they are parallel, so they add them up. They're parallel because they go from the mass to the same point and they're aligned in the same direction. But by the way, if this hypothetically this spring was tilted, was at an angle, then you have to do some additional calculation. You just can't add these up. So the moral of the story is that this is going to be the uh, effective stiffness of this assembly. Needless to say that if you had this problem and you wanted to find natural frequencies of vibration, if you move m down a little bit and let it go, it will oscillate up and down, and the natural frequency is still square root of k over m. M is m, but k is the effective stiffness, which has to be calculated by lumping these masses together. If you look at this configuration, these two springs, I hope you see that, these two springs are parallel in spite of the fact that drawn like this, okay? Because they're attached to the same point. They're attached to the same point on the outside. These are both ground, and in fact, they're lined up in this direction. So they are parallel. So these two actually can be replaced with a single spring of stiffness k over 2 plus k over 2, which is k. This bar itself has a stiffness in the vertical direction, which we are assuming it is, well, we are assuming it has a mass, therefore it has an I, so it has, I shouldn't say, I didn't mean that. So it has, it's not a rod like that, it's a beam, so it has an eye. I shouldn't have said anything about the eye being has to do with the mass. So anyway, so this acts as a spring, with this stiffness, and it is in parallel with these two put together. So basically, there are 3 springs in parallel here. Okay. So obviously, if you take this mass and move it down or move it up, it's going to oscillate up and down. No damper, it'll go forever. And if you wanted to find the natural frequencies, we need the effective stiffness of this entire assembly, which is right there. Okay, so here's another problem, and we have a hoisting drum. So there's a let's say a balcony here or a beam here, and on it there's drum hoisting drum which is mounted, and it's pulling something up and down. Now, first of all, notice that there are 2 flexible items here. 2 stiffnesses are needed. One of them is the beam, which we all know what it is, 3EI over L cube. We just looked at it a minute ago. But there's also this cable that could actually be extensible, and therefore think about it as an axially loaded member, and the stiffness of it we talked about in the last lecture is AE over L. Area cross section, E is the Young's modulus of the cable, over L. L is the length of the cable that's hanging. So you think about it, there is a beam because there's a spring due to the beam, and there's a spring due to the rope, and these are actually in series. Okay, think about it, they are in series. So these things, don't add them up. You go based on the formula 1 over KB plus 1 over KR and flip that result, you're going to get this effective stiffness. So right there. So we know the stiffness of the beam, we know the stiffness of the rope or the cable, and these are in series. These two are in series. Therefore, the equivalent stiffness of the entire single degree of freedom structure, this hoisting drum problem, is 1 over KB plus 1 over KR. It's equal to 1 over equivalent stiffness. And then once you calculate this, you flip it, you're going to get K equivalent. Here's another situation. You have a lifting crane. So we have, think about it as there is a spring due to this structural component, and there is a spring due to this cable, and it looks like that, but these are not in parallel, okay? So yes, they go from the same point to the ground, but in order for them to be able to add these up, they must be kind of parallel, really parallel. In order to get the effective stiffness of this, you have to do some energy method, for example, or some longer static analysis calculation. Either way, don't just add these up. These are parallel, but not in the sense that you can add them up. Okay. All right, so now we go to the new topic, which is the energy method and dealing with effectively conservation of energy. Now, first of all, you have to realize that the system that you're dealing with must have the energy in it must be constant if you want to go that route. This is an alternative method for finding the equation of motion, and therefore, once you get the equation of motion, you can find the natural frequencies of vibration. But if you're gonna use this, there should not be any energy dissipation, for example, in the form of frictional losses or viscous losses, or there should not be any external forces which actually pump energy into the system. For example, if you think about a fan sitting on top of a table, and this fan is uh, because of the mass imbalance just causes a harmonic force acting on the table, you're pumping energy into the table. Okay, so we're assuming there are no external forces pumping energy into the system, and there are no damper, there are no losses that are can be accounted for. Now, the whole idea is to say the total energy, which is made of two pieces, kinetic energy and potential energy, is constant for such systems. So if that is the case, kinetic energy plus potential energy for the system is constant, then we can say the derivative of that is equal to 0. So these two are saying the same thing. So the whole idea of this method is uh, finding the expression for kinetic energy, find the expression of potential energy, and differentiating, setting it equal to 0. This will actually give you the equation of motion. Okay. Now you might say, well, why do we have to go this route if we already know how to do some of these problems with Newton's second law or Newton-Euler's approach? The thing is that for the simple problems that we're doing here, Newton's second law is fairly straightforward, or we can use it. But when problem becomes slightly complicated, more complicated, then that approach may not be feasible because it involves, for example, if you look at an assembly where some certain components are attached to each other, then to do the Newton's second law, you have to isolate each one of these pieces, draw the free body diagram on it, and then write the equation of motion for each one of them, together with the interfacing forces that you get. If you go this route, you do not have to draw free body diagram, or you do not have to do it for for complicated problems. Okay, so let's look at the very first problem that we would like to consider. Very simple. We already know the answer, mx double dot plus kx equal to 0. Whatever we do, we will get that equation. I want to show you first a longer way of doing it, where we look at the static deflection and the gravity and things like that, try to get the expression for T, kinetic energy, and U, potential energy that way, and then show you that in this problem, the, the contribution due to gravity is just going to disappear, which we already know because a mass spring system like this, G is not important in it, should not appear. But here is the situation. Let me go back here. So suppose we have a spring and you suspend it from the ceiling, and this is an unstretched length of the spring. So the spring, no weight is added to it, it's unstretched like this, by this amount. If you add the mass to it, it will slowly deflect and it's go down here. This is the static deflection. So let me start measuring my x from this position, from this datum. So if I move the mass below this red line, by x of t, and let it go, it's obvious what's going to happen. It's going to oscillate up and down above that red line. By the way, in the configuration in the middle here is redrawn down at the bottom right corner. The weight of the block and the spring force, which is K delta, they are equal to each other. We know that in the equilibrium position. So let's go ahead. So when you look at an arbitrary position of the block, what can we say about the potential energy? First of all, there is potential energy already stored when we look at this configuration. You see that? Because of the fact that the spring has stretched already by the amount delta, there is some energy stored there, 1/2 k delta squared. But on top of that, there is a stretching of the amount x. So now the amount of stretching is delta plus x. So the energy stored in the spring in this configuration, where it's reached displaced, is going to be 1/2 of k times delta plus x squared. Okay, so let's go ahead and write it. So spring is going to be 1/2 of k x plus delta squared. But if this is my datum, and you're measuring potential energy from this datum, when the mass moves by the amount, or the weight goes by the amount x below it, from your first year mechanics, you know that the potential energy lost is mgx, but because it's going down below the datum that I'm going to be measuring it, it's minus mgx. But keep in mind that mg is simply k delta. So what I have done here, I've taken this mg and replaced it with k delta. So this is obvious. From here, this mg is k delta because of what we know at the bottom right corner. Okay, so this is the total potential energy. Now, as far as the kinetic energy goes, the only thing that has kinetic energy here is the mass, which is traveling at the velocity x dot. If this is the position, x dot is the velocity of the mass, and 1/2 mx dot is the kinetic energy. So we're gonna, by the way, if you look at the equilibrium position, I'm writing this thing, although it is not necessary, because based on what I have up here, we can actually proceed, add these up and differentiate it and set it equal to 0. But I want to show you something. This is this thing plus t, u plus t, is the total energy at time t. When you add these up, that's total energy at time t. But that doesn't change. So if you look at the total energy at equilibrium, when it was not moving, that kinetic energy is 0. So, and at that equilibrium point, the only energy that's stored is due to the delta. So the sum of these two is equal to the sum of these two, which is going to be showing on the next transparency, okay, next slide, okay? So this is the potential energy. This is the kinetic energy at arbitrary time t. This is the potential energy, and this is the kinetic energy at the equilibrium point. So we know that this is constant, but if you wanted to know what is the value of it, it's right there. It's this value. But anyway, we're going to clean this up. And what do I mean by clean it up? Notice that you can take this x plus delta x squared and expand it. Expand it using the stuff that you learn in algebra. Just expand it. You're going to get 1 half kx squared. But you also have 1 half k delta squared, which cancels the term from the right hand side. So 1 half of k times delta squared, you also have it on the right hand side. They cancel from both sides. Also here you have 1 half of k, 2x delta. In other words, 1 half of k 2x delta is the same as kx delta, which actually cancels this term. The moral of the story is that if you take this and you clean it up, actually you're going to get that equation. Now differentiate both sides with respect to time. So if you differentiate x squared, you're going to get 2x x dot. If you differentiate x dot squared, you get 2x dot times x double dot. This is just a standard chain rule. And clean it up. Just the 2 and 1 half cancel each other out. And divide through by x dot, and you're going to get your equation. Now notice that I could have done this thing faster by measuring x from the equilibrium position. And if that is the case, notice that the effect of gravity actually canceled out because of the cancellations here. What I could have done is said, okay, if I measure my x from equilibrium position, then the kinetic energy is 1 half mx dot squared. And if I look at that equilibrium position, the energy in it is 1 half kx squared. Okay, so I don't have to bring in the delta there. In other words, if you measure from that equilibrium position, that red line, you move the mass down below by the amount x. This is how much the spring is going to be stretched from the equilibrium position, and the amount of energy stored in the potential energy 1 half kx squared. Now you can add them up and say it's constant and differentiate it. And of course, when you differentiate it, you get, just like we did chain rule, derivative of this 1 half m stays, but derivative of x dot squared is 2x dot x double dot. It's right there. So 1 half and 2 kill each other, and divide through by x dot. You're going to get the standard mass spring system equation. Okay. So let me go and redo this problem for you that we looked at in lecture 4, but this time we're going to use energy method. Now, I noticed that when I did this problem for you in lecture 4, I did draw the direction of theta in the opposite direction. So now keep in mind that if this disk rolls without a slip to the right, theta would actually rotate like this. But in that lecture, on purpose, I drew it in the opposite direction. This is why when we came up with the kinematic equation, we ended up with minus sign here, right? Minus sign, x equal to minus r theta, and therefore x dot equal to minus r theta dot, etc. So if you go to lecture 4, you're going to see that there are minus signs next to r. But the reason was that I drew the theta direction in the counterclockwise direction. Now, but here I have chosen a different direction, and in fact, in class I made a mistake. I put in the PowerPoint that I had, mine is because I did a cut and paste. There were minuses here, so when I came to record this lecture, I cleaned it up. So I removed those minus signs. So there are two sources of kinetic energy here. One is the translational motion, which is 1 half mass times velocity squared, translation of velocity squared, but you also have the rotation of this object about its mass center, and we know from our second year dynamics class that the kinetic energy contribution is 1/2 of mass moment of inertia about the mass center or center of rotation times, in this case, center of rotation, theta dot square, angular velocity square. Now, if you get rid of x dot because theta dot, because theta dot is x dot over r, I just written it here. And in the class, I had the minus sign here because there was a mistake. I changed my direction, so this is good now. And the potential energy is only the one that's stored in the spring, and if it moves to the right by the amount x, so potential energy stored in the spring is 1/2 kx squared. So the sum of it is constant, therefore if you differentiate the sum, you get 0. So just plug these things in, the t plus u from the previous page, I plugged it in, and now we're going to differentiate it. You differentiate the first term, there's 1/2 m stays, derivative of x dot squared is 2x dot x double dot. And by the same token here, same routine, so 1/2 jo is going to stay. Derivative of this thing is 2 times that guy to the power 2 minus 1 times the derivative of what's in it. This is what we call chain rule. And same thing down here, 1/2 of k. Oops, there's a mistake. There's a mistake here, please. There's a 2 there. That's a mistake. I messed it up here. There should be a 2 between k and x, okay? That's a mistake. Good. But anyway, here it's okay. Uh, there must be, let me see, when you clean this up, okay, in other words, combine these two, well, first of all, you divide through x dot. X dot, x dot, x dot, they go. And realizing there is a 2 here. And clean it up. The things that involve x double dot, lump them together. The thing that is multiplied by x is just going to be kx, that's all. So the stiffness is just k, and the effective mass is the actual mass, and this is due to rotation. So this is exactly the same result that we got in lecture 4. Now, in lecture 4, because I did it using Euler's method, Newton's second law, Newton-Euler's law, which is taking moment, I had to draw the free body diagram. I have to include the friction of rolling force, etc. So it's although this is a little bit harder, but not a complicated problem. We could do it with Newton's second law, but here we did it with energy method, which is a little bit easier. Now, incidentally, how you go from there to there is that for a disk, Jo is 1/2 mr squared. Now, let's look at the pendulum problem that we did probably in lecture 3, or maybe I just referred to it, I can't remember. I'm not sure. We did the inverted pendulum today, and the pendulum today, it was harder because there was a spring there. But that, anyway, we're going to do this thing with the energy method, classical pendulum with energy method. We are assuming that the rod's mass is negligible. Okay, so when you tilt the pendulum, the mass goes above the datum, it gains, this is the equilibrium position, right? This is the equilibrium position. It gains energy, potential energy. And the amount of potential energy that it gains is the weight, mg, times that height, okay? Now, you will see that the gravity does have an effect here. It'll come up with the formula natural frequency. So although there's no spring in this problem, but the restoring force is actually due to gravity. When it comes to kinetic energy, is just 1/2 mass times velocity squared, but we know based on the stuff that we did we know if this angle is theta, the velocity of the mass, this is based on the stuff that you did in second year dynamics, the velocity of the mass is L times theta dot. That's what we did here, second year dynamics. And the only potential energy that we have is due to the gain in the potential energy because the mass goes above, or the weight goes above the datum. So it's going to be uh, mg times this height, and this height is simply from basic trigonometry, is the length of the pendulum times 1 minus cosine of theta. Look, this is not hard. So if you look at this height, is the total height, which is L, minus the projection of this L on the vertical direction. So it's going to be L minus L cos theta. And put together, it looks like that. Okay, excuse me. So add them together. It should be constant. Take the derivative of it, set it equal to 0. So you have to differentiate this. Notice that there's 1/2 m and there's an L squared. Those are constant. We don't have to do anything. But the derivative of theta dot squared is going to be 2 theta dot to the power 2 minus 1 times theta double dot, chain rule. And if you differentiate, for example, MGL, you get 0 because this is a constant. But MGL times cosine, you differentiate it. The cosine derivative is minus sine. Don't forget to multiply it by theta dot because theta is a function of time and you have to use the chain rule. Derivative of cosine of theta is negative sine of theta times theta dot. So we get this expression, and because we are dealing with a small angle oscillation, sine of theta is approximately theta. Otherwise, the pendulum equation is nonlinear. Okay? But if you assume that sine of theta is theta, you get this expression. This double dot should be on top of theta. Okay, and this is the standard form for this is the mother of all equations, where the stiffness, effective stiffness, is actually that L. There is no spring here, but L shows up because this, there's a restoring force to gravity, and then an effective mass is, you have to use G for it. I mean, basically, that's where it is. Now I'm going to go and do this problem, which was done in lecture 4 also, except that we're going to use energy method. So we will be using this angle theta as the degree of freedom. It's a single degree of freedom. Once you give me this theta, I know everything about the assembly. You could have used the vertical distance displacement of this right point, but that would have been another alternative way of doing the problem. But the natural one is using this theta. So the free body diagram incomplete because there is a reaction force here which I didn't draw. And we are assuming this is the horizontal position, by the way. That's why we're ignoring the effect of gravity, etc. I'm not even drawing mg here because we are assuming this is the equilibrium position. So if this tilts, there is this spring on the right hand side is going to get compressed, so there exerts a force in the upward direction, kx2, and if this spring on the left side is going to stretch, so it's going to try to pull the bar down. By the way, we are assuming that the bar does have a mass because we are looking at JO. As soon as you say JO, that means that you are actually using the polar moment of inertia of the bar about that point. Okay, it's not a massless bar. Okay? Because I'm writing JO here, I'm going to be using it. But the only thing is that uh, this x1 and x2 are related to theta, as x1, for example, is a theta, and x2 is b theta, b theta. Okay. All right, so let's see now. Kinetic energy is 1/2 JO, which means we are looking at the mass of the bar, by the way, as I said, theta dot squared, we know that. And the potential energy, the only potential energy is stored due to these two compression and tension, 1/2 kx1 squared, 1/2 kx2 squared. But we know that x1 and x2 are related to theta through these formulas. Now remember, mg, we are not taking into consideration the change in potential energy of the bar, although it's moving down, because we are assuming that this horizontal configuration is the equilibrium position, okay? And if we did take mg into account, it will cancel out because of the static deflections and things like that. Just like the very first problem that I did in this section, I took the spring, suspended it from the ceiling, and I said, well, let's attach a mass to it. It's going to deflect by some amount. That's going to be static deflection, and then from that point on. But that static deflection and the mg, actually, they cancel each other out in the derivation. It's the same story here. So we just matter of taking x1 and x2, putting it in u. We're going to get this expression and cleaned it up. We're going to take the sum of the two, and derivative of it equal to 0. Just put here t plus u from the previous page is right there, and you use your good old chain rule here to do this differentiation. The 1/2 disappears because there's power of 2 here. See that? 2 and 1/2, they kill each other. And divide through by theta dot, and you're going to get your standard vibration equation, m like mx double dot plus kx, and there's no damping here, equal to 0. Okay. Now the m effective mass is this JO, and the effective stiffness is that k times a squared plus b squared. The same result that you got before. All right. Now, so far, the problems that we have looked at, we did not include the effect of the spring in certain problems. Okay? The spring, we did not include the effect of its mass. So I want to show you what happens when we when we when we look at the problem where the spring is has a is a heavy object. Okay, for example, the stuff that you use in buildings, you know, foundation, even some suspension, car suspension, etc. They're not thick springs. If thick springs, they may have a you know non-negligible mass. Okay, so we want to see how that's taken into account. Now, in the class, I didn't actually go through this thing in detail. I just skipped through the expressions that allow you to get to the final result. And I said that, look, the final result of this problem is important. You should understand it. But the actual derivation, I want to do it, show you now, and spend a little bit more time to it, but didn't do that in class. All right. First of all, let's assume that the mass of the spring is ms. If you take a tiny piece of it, for example, of length dy, a tiny little piece of length dy, so dy, see, this is dy right there. Go to y plus dy. For example, if this mass, you look at the mass of this, it's a portion of the mass of the spring, which has to do with dy over total length. Okay, total length of the spring, if it's L, and dy is just that piece. The mass of this little piece is actually a portion of that, dy over L times ms. So that piece has this mass. Okay, now because it has a mass, it has a kinetic energy. Okay, we are assuming that everything moves with the same speed as m, okay? And the speed of m is x dot. So we take this, well, actually, I have to be a little bit careful. That is not true. What I said is not quite true. So you see, for example, what is the mass of this point on the spring? Not the mass, the velocity of this point on the spring, 0. The velocity of this point on the spring is the same as the velocity of the block. So if you look at an intermediate point, the velocity of that point is just like it was for the mass, is a proportion of the velocity of the block. Velocity of the block is x dot, no problem. But if you look at y equal to 0 on the very top, you have 0 velocity. If you look at y equal to L at this juncture, you have the same velocity as the block. So actually, the velocity of that tiny little piece is going to be y over L x dot. So if you want to find the kinetic energy of that, this is the mass of it, of that little piece. This is the mass of it. This is the energy of it. This is the velocity of it. So take this mass, multiply this by square of this, and then take a 1/2 right there. So the mass, ms over L dy, which is right there, velocity squared, and you have to do that for every tiny bit of this spring. That means you have to integrate from 0 to L. This is a standard thing for integration. And if you clean this up, you get 1/2 ms, mass of the string, divided by 3 times velocity of the block. So this is an additional term to the kinetic energy of the block, which is 1/2 mx dot squared. So you have to include that. It's the additional extra term to be accounted when it comes down to t. You add 1/2 mx dot squared to this. So effectively, it's right there, spring and the block. This is the kinetic energy. So what we're doing, we're adjusting the mass of the system by a third, by adding a third of the mass of the spring to it. So if you look at the natural frequency of vibration of this, if the spring is kind of bulky, then it's going to be in the denominator, you don't have mass, but you have mass over 3. Now remember, this is an approximation. Okay? These are first order approximations, which is okay, but I mean, you have to be careful when you're using these things. For example, if you look at the problem where you have a rod of mass m bar hanging from the ceiling, and you have a mass at the end, and this is, for example, vibrating up and down, the mass that you use in that expression for natural frequency is going to be the m plus a third of m bar. Okay, and the same thing here if it's doing the transverse vibration. So now when it comes to m, effective is going to be the mass of the block at the end plus a third of the mass of the spring, which we know what it is, by the way. Whatever it is, you take 1/3 of it. Okay. Now, when you look at the torsional spring, mass is not important, but mass moment of inertia is important. So be careful. If you look at this spring, the spring is right up here, this column. Okay, whatever the mass moment of inertia of this is, take a third of it and add it to the mass of this. But this is not the mass, because torsional is J. It's mass moment of inertia about the mass center. Okay, so it's going to be the standard J plus 1/3 of this guy. For the shaft is, you know what the formula for the I of the shaft is. Okay, yeah, I of the shaft. Okay, this is polar moment of inertia about this axis. Now, this problem I skipped in the class. We're running out of time, but I would like to discuss it here. So this is the manometer. In a manometer, again, the restoring force is the spring. No, sorry. The restoring force is gravity, is due to the weight of the displaced object, okay, displaced liquid. There is no spring here. Okay, restoring force is actually the weight due to the displaced object, and as soon as I say the weight, gravity is important. So we did this thing in class using Newton's law, but we're going to repeat that with uh, uh, energy method now. If you look at an arbitrary time t, so we have a potential energy change due to the fact that this loses energy, this gains energy because it's displaced from the equilibrium position. We take a weight and move it up. We take a weight and move it down. But the net potential energy for this thing is just these two added up. So potential energy is gamma times A. Gamma is the weight, specific weight or weight density. A is the area cross section right there. And just take half of this, half of that, add it, you get this is the potential energy. Kinetic energy, now remember, for the kinetic energy, you have to take the mass of the entire liquid because it's that entire liquid that's going to move by the amount x dot. So this is the weight, actually, the numerator of it is the weight of the entire liquid here divided by g is going to give you the mass of the entire liquid, path here, entire liquid in that, and you add them up and set it equal to 0 and just clean it up, put these things in there, differentiate it using chain rule, just like what we did before. Okay, clean it up, and you're going to get natural frequency is 2g over L square root taken. This is the same result that we got based on Newton's second law. Yeah. Uh, the last problem that I want to do is looking scary. So we have a situation like this. It says that this can be, a very crude, rough model of airplane steering mechanism for the nose wheel of the landing gear. I don't know, don't worry about what it means. I mean, you really have to look at what is it that they're telling you, showing you, and what to do. But the moral of the story is that you have a rack here, you have a rack, you have a gear which is engaged with this rack. So as this gear turns, this rack moves. Okay. So yeah, I don't particularly like the way this is drawn, although as I said, uh, the direction of theta, that's entirely up to you how you want to measure it. Okay. But if you yeah, so you got to be careful because I would have, if this thing moves to the left, if this thing moves to the left, actually this gear does a clockwise rotation. Yeah, this moves to the left, this does a clockwise rotation. So there may be a minus sign missing from the expression. This is similar to stuff that I did in the previous lecture. I can't remember, but yeah, the displacement in terms of magnitude is concerned. In terms of magnitude, it doesn't matter. This is okay. But you have to be careful depending on how you draw these things. So sometimes you will pick up a minus sign. To do that systematically, you have to look at, uh, you know, these directions are in fact affect these direction. How you draw this thing actually affects this expression. Okay, so but anyway, let's move on. So x is equal to r theta, x dot equal to r theta dot, and the same thing with the acceleration here. And if you look at this, there is a spring there and there is a spring there due to this shaft. This shaft acts like a fancy spring. And we discussed about the stiffness of a torsional shaft in the previous lecture. For example, it has to do with shear modulus. It had to do with the diameter of the shaft, okay, diameter to the 4 actually. And then there's a pi on the top, and the denominator, you have the 32 or something like that. So those you can go and check it out. And so this acts like a fancy spring, which in it has a complicated expression, pi g d to the 4 divided by 32, something like that. So anyway, we move on. Yeah. And this derivation, because we are scoring, it really doesn't matter. But this is fine. Kinetic energy comes from two sources. Translational energy of this rack, it has a mass m, it has a velocity x dot, so square it, 1/2 in the front, and you have a disk that's rotating, and the disk has a mass moment of inertia about the mass center, for example, as j, so it's going to be 1/2 j theta dot squared, okay? Now what I've done is theta dot, I can find it and replace it with x dot over r. I could have, depending on what you want your final equation to be in terms of, whether you want it to be in terms of x or theta, you either eliminate theta or x. So here I've eliminated theta by going to this equation, find theta dot right there, and just clean it up because they have common x dot squared, clean it up. Potential energy is this spring stretches 1/2 K2 x squared. This spring, fancy spring there is actually twists. So it's a torsional spring, 1/2 the appropriate K theta dot squared. And once again, you eliminate theta in terms of x from first line there and clean it up, you get this, and therefore you have the natural frequency. Well, the total is here. Total kinetic potential energy is right there. Differentiate it and set it equal to 0. We have done this thing so many times, taken this and differentiate it with respect to time, and divide through by x dot, and you get well, on the next slide. Yeah, divide through by the x dot. This is repeated here, I don't know why. It's the same thing. You get this. This is a mother of all equation. This is the effective mass. This is the effective spring. And the natural frequency of vibration is right here. Now, what this thing means, by the way, let's go back to this diagram. It means that if you move this block rack a little bit to the left and just let it go, this whole thing will oscillate back and forth. This whole disk will oscillate back and forth by rotating, by turning. They are engaged, okay? So as this thing oscillates, the gear oscillates, and the frequency of oscillation is precisely what you see there. Okay, that wraps up the lecture for today. I mean, usually when I do these things in class, it takes about 1 hour, 20 minutes, the way the class is supposed to be, the duration of the class. But when I record these, because I do it in my office, it takes, it's shorter. So today it took 1 hour, I don't know, maybe 5 minutes, 10 minutes. I'm shortchanging you here in these recordings by 10 minutes, 10, 15 minutes. Okay? Good luck. So see you this afternoon in the lab, in the tutorial. In the event that you have any questions, we're going to be there to answer it. Don't voluntarily do anything in the tutorials. And have a good weekend if I don't see you this afternoon.